Hey everyone, and welcome. So, have you ever looked at a new AI model, seen the specs, and had that sinking feeling asking yourself, can my machine actually run this thing? Well, if you have, you are in exactly the right place. Today, we're going to crack the code on VRAM and figure out what it really takes to run AI on your own hardware. And look, we're kicking things off with this question pulled right from a Reddit thread, because honestly, it hits the nail on the head. This one question gets to the absolute core of all the confusion, and it's the perfect launchpad for our whole discussion. It highlights the biggest misunderstanding out there when it comes to local AI. All right, so first things first, we have to clear this up. There's a massive difference between creating an AI model and just using one. They are two totally different jobs, and believe me, they have completely different appetites for your computer's memory. Let's think about it like this. Training a model is like writing a gigantic, complex textbook from scratch. You need space for the final text, right? Those are the model's parameters. But you also need room for all your drafts, your notes, your corrections. That's all the gradients and the optimizer states. Now, inference? That's just reading the finished book. All you need is the final published version. Just the weights. So much simpler. So what's the big takeaway here? It boils down to this super simple rule of thumb. Full-on training needs roughly 4 times the VRAM as just running a model for inference. 4 times. And why 4? Well, you need one chunk for the model weights themselves, another for the gradients, and usually 2 more for the optimizer states. It adds up, and it adds up fast. Okay, so let's be real. Most of us are just running models, not training these behemoths from the ground up. So let's focus on inference. I want you to imagine your GPU's VRAM is like a chef's workbench. To get cooking, you've got to lay out a few key ingredients. Okay, the first thing you're going to slap down on that workbench, the biggest piece by far, is the model's weights. This is its brain, its entire library of knowledge. Think of it as a giant cookbook. For a 70 billion parameter model at a standard precision, this cookbook alone takes up around 140 gigabytes. It's the biggest, most predictable part of this whole equation. Next up on the workbench is something called the KV cache. You can think of this as the model's short-term memory or its scratch pad for the current conversation. It's super important because it remembers everything that's already been said, so it doesn't have to reprocess the whole conversation for every new word. And as you might guess, the longer the chat, the bigger that scratch pad gets. And finally, you've got to leave a little bit of room on the workbench for, well, for work. This is the temporary space the GPU needs to actually do its math. Things like activations and other system overhead. It's not the biggest piece, but you absolutely need it. Now, this is the part that blows a lot of people's minds. Look at how big that KV cache can get. For a 70B model with a really long context window, we're talking 128,000 tokens, the KV cache by itself can chew up almost 40 gigabytes of VRAM. That is a massive memory hog, and sometimes it can get almost as big as the model weights themselves. Okay, so wait a minute. If a 70B model needs over 140 gigs just for its weights, how on earth are people running these things on gaming GPUs that only have 24 or 32 gigs of VRAM? Well, this is where the real magic happens. We're going to break down 2 incredible tricks that have totally changed the game for local AI. First, quantization, which is all about making the models smaller. And second, LoRa, which makes the process of teaching them new things way, way cheaper. Let's start with quantization. This is pure genius. All it does is reduce the precision of the numbers inside the model. The best way to think about it is like compressing a photo. You can take a massive, high-resolution image and shrink it down to a much smaller JPEG. Yeah, you technically lose a little bit of data, but most of the time you can't even tell the difference. And the savings here are just wild. Look at this. Popular methods like GGUF and AWQ can shrink a model's memory footprint by about 4 times. That lets you squeeze that 140 gigabyte monster down into a much more manageable 35 gigs. And newer hardware-level tricks like FP8 can cut the size in half with almost zero loss in quality. It's a game changer. All right, now let's talk about LoRa. This has completely revolutionized fine-tuning. So remember our textbook analogy? Instead of having to rewrite the entire 175 billion word book just to teach it something new, LoRa is way smarter. It freezes the original book and just adds these tiny trainable sticky notes to it. It is unbelievably efficient. I mean, just look at these numbers. They're absolutely insane. For a massive model like GPT-3, you end up training less than 0.1% of the parameters. This chart says it all. The huge part of the model is just frozen. You don't touch it. This can slash the number of trainable parameters by a factor of 10,000, making fine-tuning something almost anyone can do. Okay, so you've done everything right. You've quantized your model. It fits perfectly in your VRAM. You fire it up, but it's not as fast as you expected. Why? This brings us to probably the most surprising bottleneck in modern AI.
You see this question online all the time, right? Someone buys a new GPU with way more compute cores, but they only get a tiny speed boost. They feel like they've hit this invisible wall, and they just can't figure out what's holding them back. So what is really going on here?
And boom, here is the answer. Straight from the folks who research this stuff for a living. It's not about how powerful your GPU's brain is. The problem is your GPU is just sitting around, bored, waiting for data to arrive. The real bottleneck is memory bandwidth. Here's the simple version. The attention mechanism, the core of the AI, is constantly reading data from your VRAM. And what researchers found is that over half the time, these super powerful compute cores on your GPU are doing nothing. They're just stalled, waiting. Your speed is literally capped by how fast you can shovel data into the GPU, not by how fast the GPU can think. So knowing this, knowing that bandwidth is king, it completely flips the script on how you should think about buying hardware. Let's connect all these dots and build a roadmap for picking the right gear. This table really lays it all out. You've got a future consumer card like the RTX 5090, which is rumored to have insane memory bandwidth. That's going to be a beast for running quantized models at top speed. Then you've got something like Apple's M3 Ultra. It has less bandwidth, but offers a truly colossal amount of unified memory, which is perfect if you want to experiment with gigantic models that no one else can fit. And then, of course, you have the pro-level cards like the H100, which give you the best of both worlds for a very, very high price. All right, let's wrap this up. What are the big things you need to remember? 1. The 4x rule. Training is a memory monster compared to inference. 2. Quantization is your absolute best friend. It's how you fit today's big models onto consumer cards. And 3, maybe the most important, for pure speed, memory bandwidth is king. It's often more important than raw compute. At the end of the day, you have to choose your hardware based on your goal. Are you optimizing for speed, for model size, or for flexibility? So there you have it. You're now armed with the fundamental secrets of AI memory. You know the difference between training and inference, you know the tricks to make models fit, and you know what the real performance bottleneck is. The only question left is, what are you going to build with it?